I was going to ask you about TMG. I've been reading a lot about how that's good for blood pressure and things like that.
Hmm.
And with everything else that I've been doing, is that something that you think would be okay for me to try?
Yeah, you could try it.
Okay.
Um, Real quick, TMG is trimethylglycine. So TMG, trimethylglycine, and where it could be playing a role from a blood, one example would be where it could play a role in blood pressures in the methylation cycle. So the methylation cycle is a pathway in the liver. It's in every cell, but the liver does a lot of it, where you're converting methionine, the amino acid methionine, to homocysteine. And the reason you do that is when if these are two gears, right? This gear turns this way, which will turn this gear this way. And when this gear turns this way, methionine gives up a piece of itself called a methyl group. And once you give up a piece of yourself, you're no longer you anymore. You look different. So then methionine is homocysteine. Well, homocysteine is pro-inflammatory, oxidative stress, heart risk, kidney risk, brain risk, all kinds of risks. So we don't want to let this build up. So the body wants to, again, take it and turn this wheel and turn it back into methionine so we can just go round and round all day long here. Another pathway is the homocysteine could go down what's called the CBS, a pathway that has CBS as a gene to run it, and that can be turned into glutathione and other things. Well, the let me erase this for you. So how does trimethylglycine play a role? Well, this methylation cycle is turned by genes. So we have a gene here called MTHFR, methyl tetrahydrofolate reductase. You have one here called MTRR. You have what's called a short pathway here. So you have this long pathway you could spin, or we have a short pathway here. And there's a gene here called BHMT, and then the CBS gene. So this is an example of a few genes involved. Well, genes make enzymes, and enzymes are the proteins that do work for us in our body. So the proteins made by these various blocks, which are the genes, help spin these wheels or turn these gears. Well, the enzymes require nutrients to work. All enzymes in the body have nutrient cofactors they require to work. So the MTHFR requires folate, which is vitamin B9. MTRR requires B12. CBS requires B6. And BHMT requires trimethylglycine. So that's where your TMG could play a role. And again, methylation, the process of methylation, the reason this whole cycle we need it to spin is because when methionine gives up this methyl group, it's methylating something. So when methylation turns a gene on or off. So when it's giving up that group, it's going to some specific gene to either turn it on for expression or turn it off so it doesn't express. And so, that you could be turning on or off cardiovascular genes related to cardiovascular function and blood pressure that way, and or if you're lacking some of these nutrients, then this wheel isn't turning well, and now we have buildup of homocysteine, which is toxic to blood vessels, toxic to kidney, both of which play a role in blood pressure status, toxic to brain, which helps regulate blood pressure status. So it's plausible that issues here could be driving blood pressure that way. And so again, your question about how might TMG impact it, that's the tie-in, at
Okay.
least as what I can come up with right now.
Okay. Thank you very much.
Anything else?
I just was curious if your ability to methylate changes over time, or is that just something that is standard throughout your life?
No, it absolutely can change over time because again, for this cycle to happen requires these nutrients, right? And our nutrient levels are constantly changing, especially with B vitamins, because B vitamins are water soluble, meaning they peak in the blood 1 hour after we take them, and then we spill them in the urine after that. So those of you, everyone on here has worked with me. So, many of you have experienced when you take the multivitamin, your pee turns neon yellow or neon green, and you're like, what's going on? Well, those are the B vitamins coloring your urine. You're spilling those. And so, if you went too long without optimal B vitamin status, then you don't have the substrate for this cycle to turn well, and then you're not turning your genes on and off well, you're not methylating well. So yeah, your nutrient status directly influences how efficient this is. It's one thing that does. And then of course your genetics do as well. So each of these boxes, again, are genes, and they're made up of two alleles, which basically we get one half from mom, one half from dad. So the MTHFR gene is a common gene where people have what are called SNPs, or single nucleotide polymorphisms, which is fancy for variation or mutations, which mutation's the wrong word, variation's more correct, but lay people are more used to hearing mutation. So if mom and dad both gave you a good copy, then you would have a minus minus presentation. If someone gave you a bad copy and someone gave you a good copy, it'd look like that. If you had two bad copies, you'd have two pluses. Well, in regards to the MTHFR gene function, this is ideal. This is normal, right? This confers up to a 40% decreased efficiency. Two bad copies gives you up to a 70% decreased efficiency in this cycle. So you're not damned to it. This is epigenetics. Okay. So if you have two bad copies, it doesn't mean you're damned to a 70% reduction in function. Your increased susceptibility to that. I've had patients with two bad copies that have perfect homocysteine, so they're functioning well from an MTHFR standpoint. I've had patients with two perfect copies that have terrible homocysteine. So they would be worse off than the patient with two bad copies with normal homocysteine. So the genes are a susceptibility, but the real-time data comes from your homocysteine level. Like how is this functioning in real time for you? Look at the homocysteine.